All right, here we are again. Very good. So what are we doing today? All right, well, first we're going to look at this practice problem set. These are cases where we're evaluating functions at different values. And in some cases, if you notice, the values themselves are actually constants, which makes it a little bit more tricky, but it's certainly not impossible to do this. When we're done here, we'll go back to chapter 1. And let's see, if I remember, we left off roughly where we were evaluating functions. And no, we started to solve functions as well. Okay. Let's see, where did we? Oh, we were looking at all these different functions, one at a time, looking at their graphs and understanding their key properties. And oh, okay, I think this is where we may have left off, where we were starting to try to figure out how to determine the domain of a function. Okay, sometimes it's really straightforward, but sometimes it's not. Okay, so we want to get some more practice understanding how to identify the domain of a function. And let's see, there's a few other key topics we want to look at here, and then we'll go on to chapter 2. Although I do have a couple of fun videos for us to watch today that will help us understand a little better the history of math, and I think you'll find them to be extremely interesting. So I'll tell you what, let's go take a look at Moodle. And let's see what's there waiting for us. Let's see. Oh, okay. Oh, here it is. Okay. All right. So we have chapter 1, which we're partially finished with. And then we have chapter 2 coming up. And then we have down here, these are the 3 videos that I'd like to look at today. But first, let's take a look at the practice problems and see how we did. Okay. And then when we're done, you see there's 2 others, practice problems parts 2 and 3. By the end of today, you should be ready to do these as well. Okay, so what I'll ask you to do when we're done is work on these for next week. Okay, and I'll remind you before we finish. All right, so I think our first priority here is to get to these problems, just to make sure, like I said, that you're keeping up and you're understanding what we're doing. If not, well, now's the time to find out and time to get some more practice. So let's get started on this. Hold on one second. Make it a little bigger for you. Get this out of the way. All right, so why don't we begin it? So here's what you're supposed to do here. For example, in this first one, you're going to take f of -3, which means that every x in this function is replaced by a -3. Okay, so therefore we have -6, -5, and our final result is -11. And that's really all there is to it. Okay, now some of these are trickier than others, of course, but ultimately this is what you're doing. Now, f of 2 would therefore be 2 times 2 minus 5, which is 4 minus 5, which is, of course, -1. Now, this is where it gets a little more strange and bizarre. A is a constant. So with these, often you'll wind up with some expression that can't be evaluated any further. So for example, here, this is as far as you can take it. Okay, and that's it, you're done. I know it seems a little concerning that you can't go any further, but that is actually all that you can do with it. And then we also need to do negative f of a. So basically what you're doing here is you're actually calculating f of a. And just copy this down here. So the key detail here is that the negative comes on the outside of this expression. Okay, so you're going to wind up here with -2a plus 5. So it's not the same, is it? So here, with this one, all the x's are replaced with a's, negative a's, I mean. Whereas here, you're actually solving for f of a, but then applying a negative to the result. So therefore, that's why it looks like this. And now this one's a little more challenging. F of a plus h. And again, those are both constants. Okay, so what you're doing is you're replacing the x with a plus h. And now you can apply the 2 to both terms inside those parentheses. You end up with 2a plus 2h minus 5. And that's it. All right, now if only they were all this easy. It doesn't quite work that way though. Yeah, they're going to get a little bit messier as we go along, especially when we start getting involved with squares and square roots. So it's kind of unfortunate, but we can do it. Okay, so like for example, let me just do one thing here. Split the screen. I don't want to have to keep running back and forth a million times from the top to the bottom. So let's get this here. All right, now what happens here? F of negative 3 will therefore be minus 5 minus 3 squared plus 2 times negative 3 minus 1. And so now we have to be careful with this one because you're multiplying negative 5 times 9. I just want to do that one in 2 steps. Minus 45 minus 6 minus 1 equals minus 52. Okay, so that's how that one works. So you have to be careful with it. Make sure here you're squaring the negative 3, then you multiply by negative 5. Over here, you're subtracting 6, of course, and 1. And so ultimately, we wind up with negative 52. Okay. By the way, these solutions will be posted on Moodle, rather, when we're done. So if you miss something, it'll be there. And then you can also watch the video, and you can always ask questions, of course. All right, now, what about this one? So f of 2 would be minus 5 times 2 squared plus 2 times 2 minus 1. So it's minus 5 times 4 plus 4 minus 1 minus 20 plus, whoops. Minus 17. Okay. Minus 20 plus 4 is minus 16. Then we subtract 1, and we end up with minus 17. Beautiful. All right, now, this is where it's going to get a little messy. When we start dealing with the constants, because there's a square here, f of negative a equals minus 5, 8 minus a squared, okay, plus 2 times negative a minus 1, minus 5. Now, negative a squared, of course, is simply a squared. So we'll leave that as negative 5a squared minus 2a minus 1. And that's it. You're done. So it's a quadratic expression, which you would expect because the original function was a quadratic expression. And since we don't know the value of a, we can't take it any further. Okay, now how about this one? Minus f of a. So here's what I recommend you do. Put a minus out here, and then inside the brackets, calculate the value of f of a. Okay, so you notice what I'm doing here is I'm replacing the x's with a, but the negative stays on the outside. Okay, so here's the negative. And what's in the brackets is actually f of a. I just think it's easier that way. So you're going to have negative, now inside the brackets, negative 5a squared plus 2a minus 1. And then I can evaluate this with the negatives. In other words, I'm going to apply the negative to each term inside the brackets. So this first term will be 5a squared. Then the second term will actually become a negative, and the last term becomes positive. All right. So finally, we have the really scary one, f of a plus h. So yeah, that's going to be a bit of a headache. You'll see why in a second. Okay, now the only reason this is the least bit scary is because a plus h squared could be written as simply a plus h times a plus h. And once you do it that way, you can see that you can actually apply FOIL here. Okay, let me copy this to the next page. Again, so I don't want to be constantly scrolling back and forth. So let's apply FOIL to this. So F is the product of the two A's. In fact, let me just write this in here for a second. Just a quick reminder, this is F. This is O. This is I. And this is last. Okay, so now it should be pretty clear what we're doing. So F is A squared, O is AH, as is I, and last is H squared. Let's get this out of the way. All right, so when we bring them together, what we've proven here, or demonstrated, is that this expression could be rewritten as a squared, let's see, plus 2ah plus h squared. So that being the case, right here, what we can do now is rewrite it as -5, and in parentheses, I'll have all of this. Okay, so we'll start with that. And now I'm going to distribute, so to speak, the -5 across these terms, as well as the +2 across these terms. Okay. So I'm going to ultimately end up here with -5 a squared minus 10ah minus 5h squared plus 2a plus 2h minus 1. Now, what we're going to do here is look for any opportunities to combine these terms, but I don't see any like terms that we can add together. I think we just have to leave it like this. Ooh, that's unfortunate. So what will often happen is we may just leave it like this, because if you notice, distributing it didn't help us simplify it all. So you could put the answer as either one of these two. Okay, so either one is fine. If this made it simpler, then you certainly want to do that. You always want to simplify your answers whenever possible. If it's not possible, then it's just not possible. That's what are you going to do? That's just the way it is. All right. That was the last one, wasn't it? Yes, f of a plus h. Now, the next one, though, has a square root. So that's going to make it even a little trickier. Okay, so let's do this. Let's see. We'll start with f of -3. I'll do this one by hand because it's a little quicker than the equation editor is wonderful, but it takes time. So 2 minus -3 is, of course, +5. So this one is ultimately nothing but, oh, sorry, my fault. I just realized I misread it. No, that is not correct. I just noticed that now. That's better. Okay, I accidentally put the 5 under the radical sign, as you can see. So it's 2 minus -3 radical of 2 minus 3 plus 5. Okay, that's more like it. And now we're done. Okay. How about f of 2? Oh, sorry, that's 2. My fault. No, I did it again. There you go. There you go. All right, this one works out very interestingly because you've got now the square root of 0 plus 5. Okay, yes, Fernando, go ahead.
You said that we could simplify when it comes to these type of equations, right? And then
Yes, always simplify whenever possible.
couldn't you simplify the first one, f of -3, to like the square root of 10 when you simplify that?
No, because this is on the outside. I almost did the same thing myself a minute ago. That's not correct because it's not inside the square root sign.
Oh, okay. Thank you.
Now, there are things you could do. Like, I guess I shouldn't say that it's not possible. For example, if you were determined to combine these two, you could take your 5 and let's see, what could you do with it? I'm not sure. No, I guess not. I mean, I'm not really sure if there is any way of doing this. I think it's fine the way it is. Let's just say that it's not worth the trouble to find a simple. This is as simple as it's going to get. Let's put it that way. All right. So yeah, you have to be realistic with the simplification. Sometimes there's so much trouble that don't bother. The whole idea is just to make things easier for ourselves. So if the simplification is a mess, just don't bother with it. Like up here, for example, it turned out not to be worth our while to simplify this one because it didn't help simplify. In other words, none of the terms combined with each other. So you would often see it left like this. Here, I would just leave it as radical 5 plus 5. All right, now here, what we're doing is we're going to have radical 2 minus a. So this one is very simply 2 plus a under the square root sign plus 5. The next one, now again, negative f of a. What you're actually doing is putting a negative sign out here. Now you're going to calculate f of a. So, oops, I keep forgetting. It's radical 2 minus x. We're going to get a space here. Hold on. There we go. Okay. I want you to be able to see it all in one shot. Okay. Now that negative applies to the entire expression, even the 5. Okay. So we end up here with negative radical 2 minus a minus 5. Okay. And one more. F of a plus h. So you have to be careful here. A plus h is all in parentheses. So we're not going to be able to do too much with it, but we can simplify it a little bit. Although it's not really absolutely necessary. If you apply this negative, you can see it's not radically improved. And that's it. That's your final result. So yeah, this one wasn't easy to simplify, but they're done. Now, this one could be a potential nightmare because we've got division here, and we have to be careful to make sure we do not end up with division by 0. So why don't we start with the first one? So you can see literally all we're doing is replacing the x's with -3s. Okay. And we're hoping that we don't end up with a mess. Okay, it's possible that we'll end up with a mess. As long as we don't end up with a result that is undefined, like division by 0 or the square root of a negative number, we should be okay. This is -18 minus 1 over -15 plus 2. So -19 over -13, we can simplify that to +19/13. Okay, that wasn't so bad. All right, very good. Now f of 2. So we'll have 11 over 12, and we're done. All right. Which one are you referring to, the first one or the second one? So in other words, here, -19 over -13, the two cancel each other out. The negatives cancel. In the second case, both numbers were positive. Okay. All right. I have to be careful with this one. I'll tell you what, I'm just going to copy this onto the next page. Again, we do not want to be scrolling back and forth. So this time we're looking for f of -a. And in a case like this, there's not a whole lot you can do with it. Sometimes these, they can be reduced a little bit, but not in this case. I don't see any way we can simplify it any further. So, don't waste your time looking for the perfect simplification. If it's obvious, go ahead and do it, but otherwise, this is fine. So now here again, negative. Now we're going to do f of a. Now let's do this. Let's evaluate the whole thing inside the brackets before we apply this negative. Otherwise, you're bound to make mistakes. All right, so you have to be really careful with this. Oh, actually, you know what? Let's just leave it like this. This is fine. But if you did, all right, I'll show you what it would have looked like. Either one is fine. Okay, and then finally we have the a plus h. Now I'm going to multiply 6 by a plus h. Down here, I'll do the same thing with 5. It isn't absolutely necessary because it's not simplifying anything, but I think we'll do it anyway. All right, that should do it. So far, so good. We're all getting these correct. Or not. I hope everybody's getting them.
For negative f of a, wouldn't the bottom one be -2?
No,
Wouldn't
you only apply it. If you did it twice, you'd end up canceling out the negative. So you can only do it to the top. Okay, it's like let me show you an example of that. It's like this one. Okay. Well, even if you didn't get them right, at least you see what happened. If you did them wrong, you understand now. So, all right. Anyway, so now the last group, part 2, luckily these are all constants. There's no more A's and H's. That's done. Okay, so we're all happy about that, I bet. Because it's very abstract that way, but it's a good skill to have. You can deal with these abstract expressions. All right, here we go. Hold on, let me split the screen. And let's see, what do I want to do? All right, let's start with the first one. Okay. Oh, these I can type. I might as well type them. It's a little faster. And neater, I guess. All right, so for example, here, f of -2 equals 4 minus -2. 4 plus 2 is 6. Oh, no, wait a minute, what did I do? I'm sorry, this is not right. It was 2 minus 2. Ah, okay, no, I royally messed that up. Okay, so yes, in other words, the -2 is the x. So it's 4 minus 2x. The x is replaced with -2. That makes it 4 minus -2, or 4 plus 4, which is 8. f of -1 would be 4 minus 2 times -1. That's 4 plus 3, which is 7. Oh, no, what did I do? 2, sorry. That was a typo. 6. Now, by the way, by doing it like this, if you notice, it's -2, -1, 0, 1, and 2. The purpose of doing it like this is that you notice something, a pattern that's emerging here. What do you notice about these? As the x goes up by 1, the function goes down by 2. So in other words, if I keep increasing x by 1, f of x will keep going down by 2. Now, you might have recognized that this is a straight line. If you were graphing this, you might write it as y equals, let's say, -2x plus 4. -2 is the slope, and 4 is the intercept. So in other words, when the slope is -2, and just throw this in here as an explanatory note, the slope is -2. When x increases by 1, y decreases by 2. And that's why this is happening. So you notice I keep adding 1 to the x, and the result keeps shrinking by 2. So if I asked you for f of 3, you wouldn't even have to do the calculations. You could see that it's simply going to be -2. Ah, see that? So there was an important idea hiding behind this one. The slope can tell you how the function should change when x changes. If you didn't notice that, that's fine. Now here, see, now look at this one. You're going to see the same thing. The slope is -3. So watch what happens. I start with f of -2. $14. Okay. Now what do I have with -1? It goes down by 3, doesn't it? Yes, it does, and it will keep going forever. Here's a little trick that I learned. I can put them together so you can still see them. And so every time I increase the 1, what happened to f of x? It went down by 3 because the slope is -3. Interesting. Okay. Now the next one, well, sorry, we can't, not yet. We'll see how this works later on, but this next one is a quadratic expression. So that pattern is going to be, let's just say, not the same. We'll get to this eventually though, but -2. So remember, all the x's are replaced with -2. So it's a little bit trickier here. You're going to have 8 times 4 minus 7 times. Well, we'll leave it like this, okay, just for now. Uh, 49. Wait a minute. Oh, I just, no, wait. Hold on a second. 2 minus 7, -2 plus 3. Yeah, I want to make sure I didn't goof it up. 8 times 4 minus 7, -2 plus 3. And that would be 32 plus 14 plus 3, 49. Okay. Okay, now, what about -1? Okay, so I'll have 8 times 1 minus 7 minus 1 plus 3 equals 8 plus 7 plus 3 equals 18. 0, this is easy. It's always easy with zeros. I like zeros. Okay. All right, 1. Oops, 8 times 1 squared. Minus 7 times 1 plus 3. Oops. 8 minus 7 plus 3 is 4. And finally, f of 2 is 8 times 2 squared. Minus 7 times 2 plus 3 equals 8 times 4 minus 7 times 2 plus 3 equals 32 minus 14 plus 3, 21. Very good. But here it would be difficult to identify a pattern. That's because it's a quadratic expression. You do not have a constant slope like you did up here with the straight line. So it would be very difficult to identify a pattern, or at least not until later on in the course when we understand quadratic functions a little better. All right, you don't have to look for patterns. It's just sometimes it's interesting to notice them. It's not necessary. All right, now, I think there's just one more, 8. Oh, square roots. All right. Well, we'll have to tough it out and do the square roots, even though they are kind of a nuisance. All right. So we'll start with -2. Okay, so of course the square root of 1 is just 1. Very good. F of -1 is 3 plus -1 plus 3. Now it's something like this, 3 plus radical 2, there's nothing you can do with it. You have to leave it just like that. F of 0 again, there's nothing we can do with this one to simplify it. f of 1, 3 plus 1 plus 3. Now this one is different. You can reduce this to 5, which is kind of nice. And then finally, at long last, we're almost done. F of 2. 3 plus radical 2 plus 3. And again, this is one of those cases where there's nothing we can do to simplify it. It's simply 3 plus radical 5. All right, well, that was pretty tough, but we did it. And so I will be posting these solutions, and you can double check your work if you are not sure. Let's see, one thing I do want to do. One of the annoying things I find about Word is that it does not give you page numbers unless you specifically ask for them. I think that is so stupid. I hate having a long document without page numbers. So I always double check, or at least I try to. Because if you don't, you know what's going to happen. You're going to drop these on the floor and you'll never get them straightened out again. There it is. Okay, we're good. All right, so we'll put these away now. And okay, so don't forget there is a second and a third one, which we should be ready for this by the time we're done today. In the meantime, though, I think we need a bit of relaxation. Why don't we watch these 3 videos? They're very, very useful and helpful looks at the history of math. And I think you'll find them to be extremely interesting. Now, here's what we're going to do. It's been my experience that if I try to show this to you on my screen, you may not be able to hear the sound. Okay, so what we do instead in these cases is I'm going to send you the link in the chat room. And what I want you to do is watch it on your screen. Okay. And in the meantime, I'm going to turn off the sharing so that the sound on this side doesn't distract you. So where's the chat room? Here it is. All right. So here it is. So check it out. And I think you'll agree this is an extremely interesting video. All right. So I'm going to stop the sharing until it's done. And go ahead and watch it. And then we're going to go over it when it's over. And I think you'll agree that was pretty cool. All right, is everyone done watching it? Okay, yeah, I don't want to rush you or anything, but do you agree that was a pretty cool video? It was certainly very interesting. I mean, the thing is with like instructional videos like this, or I guess educational videos, I should say, it's not always easy to achieve a good balance between rigor and fun. I mean, I think you'll agree that whoever did that video did an excellent job bringing it to life instead of making it very boring. But yes, zero turned out to be an incredibly important discovery, and it did take humanity many centuries to come up with the idea because I mean, in the early days of humanity, what were numbers used for? To count things like how many crops, how many bushels of wheat have I planted this year, you know, or how many chickens do I have, and things like that. And why would we ever need a zero? It was just not clear until mathematicians in the, I think he said it was the ninth century, or she said the ninth century, came along and said, you know, here's what zero is supposed to be, here's what it's for, and here's how it could be incredibly useful. And of course, the Romans, you might remember from high school or whatever grade it was you were learning the Roman numerals in, the Roman numerals did not include a zero. They hated the idea. They didn't think there was any need for it. And that's one of the many reasons why we don't use Roman numerals anymore. Certainly they didn't have negatives either. It was a system that was fine at the time, but it was never going to be useful for what we needed to do now. So the Arabic numbers are the ones we're actually using today, you know, with some help from India too. Now, the next video is about zero as well, but specifically it's an explanation, which you may not have thought about before, as to exactly why you're not allowed to divide by zero. I mean, everybody's always told you you may not divide by zero, but they may not have explained to you why. Okay, it turns out that if we allow division by zero, we would have chaos because all the numbers would actually be equal to each other. I mean, it's hard to believe that, but you'll understand when you've seen this video. And it's also very well written. It's very interesting to watch. It's fun, but it's also extremely important because it really explains in great detail exactly what the problem is with division by zero. Okay, so I think you'll really like this one. So let me go get the link. Let's see. Why can't we divide by zero? Hold on one second. I'm sure this has been keeping you up at night worrying about it. No, but I mean, now you get to find out exactly why. All right, you don't have to just take anyone's word for it. You'll understand yourself why this can't be permitted. So let's check this out. And again, when we're done, we'll get back and discuss it. So let's check it out. Well, now that was pretty mind-bending, don't you think? You're going to be pondering this all day now, thinking about division by zero and why. And it was I thought it was a very interesting discussion as to how and why this is not possible. Although you never know with math, they always come up, like he said, with new ideas. And that Riemann sphere, which is way, way beyond the scope of this course, gets involved with the imaginary numbers. So it's not exactly the same thing, but anyway, so now you have a much better feel for what the problem is. Of course, the whole issue there is that zero can't have a multiplicative inverse, and therefore division by zero can't happen. But anyway, so there's one more here that I thought we could look at today, which is relevant to what we've been talking about. And this one is all about irrational numbers. Now, I don't think we explicitly talked about this last week. Let me just quickly remind you what that's all about. Hold on one second. I just need to get out a Word document. Hold on, what's going on here? For a minute there, my screen refused to show me my icons down there. All right, let me just get this open real fast. I just want to remind you what it means to be irrational. So first of all, what does it mean to be rational? A rational number can be expressed as the ratio of two integers. So for example, 1.8 is rational because it can be expressed as 9/5. Okay. Let's say 0.3 is rational because it can be expressed as 3/10. Negative 4.1 is rational because it can be expressed as negative 41/10. Okay. Now here's an interesting one. 0 is rational because 0 divided by any integer is 0, and 0 itself is an integer. Okay, so therefore 0 is rational. And now let me give an example of something that's not rational. Pi, our old friend from high school, pi. Oops, not that. Hold on. Okay, pi is irrational because it cannot be expressed, as you've probably been told in high school or whatever level it was at, be expressed as a ratio of two integers. Closest, occasionally you see people mentioning that, you know, it's close to 22/7, but it's not exactly. Okay, so that's what it means to be irrational. Now, all real numbers are either rational or irrational. Okay, so now this notion of irrational numbers actually caused a lot of issues for the ancient Greek mathematicians, because according to their worldview, such a thing couldn't exist. So when it was discovered that some of these numbers, for example, the square root of 2 turns out to be irrational, that caused a lot of issues. And so anyway, so the video is going to talk about irrational numbers in a very interesting way. So let me go get the link for you. All right, hold on. Oh, here it is. Okay. All right. Let's check this out. Right. How was that? So yeah, it was an interesting conflict because the ancient Greeks believed that everything in nature was made out of perfect squares or perfect circles, that kind of thing. And so the existence of irrational numbers actually threw all of that into question. And so that's why it was so controversial and why, let's just say, his I now can't even pronounce it properly. He was not appreciated in his time. Let's put it that way. So, all right. Anyway, let's see. Let's go back. Let's see. I'm trying to remember where we left off. I think we did look at all of these functions, their domains and their ranges after all. So why don't we do this? Let's jump ahead to rates of change. I don't think we did this. So let's start here. I'm pretty confident we've finished all the ranges and domains of these different functions, but we can start now with rates of change. And so the average rate of change for a variable over a given time interval is equal to the change in the output divided by the change in input. So that sounds very abstract, but you'll see as we go along that it's not that complicated after all. So first things first, this is actually just taken directly from the concept of the slope. And so you might recall that the slope of a line or any other function is delta y over delta x. But what exactly do we mean by delta y and delta x? Well, you have to assume that there are 2 points on some function, which we can draw on the xy coordinate system. For example, let's say that this is our function. We don't know what it is, but here's the point x1, y1. And here's the point x2, y2. And so the change there in y, delta y, is the difference between y2 and y1. Or we can rewrite that as f of x2 minus f of x1, all divided by x2 minus x1. So this is what we mean. This is going to be defined as the average rate of change. And essentially what we're trying to do is figure out how much did y change relative to the amount that x changed. And you could visualize if I could connect these 2 points with a straight line, the slope of that line is essentially what I'm estimating here, right? Okay. Now that isn't the best drawing in the world, but that line that connects the 2 points, its slope is this. And it's giving us a feel for how much y is changing relative to the change in x. So here's a quick and simple example. What if it turns out that the price of gas in, let's say, in New York State in 2009 was $3.29 a gallon, and it is currently $3.49 per gallon in, let's say it's 2019. What is the average rate of change over this period? So in other words, what we're trying to find out is how much has gas or have gas prices changed per year during this period. That's really what we're asking. What has been the average gas price change per year over this interval? Now, this one is so simple, you could probably do it in your head, but we want to formally go through these steps. So we have delta y over delta x. So in this case, this is the gas, f of x2 means the gas price in 2019. This is the gas price in 2009. And of course, in the denominator, we have the actual years. The key detail here is that gas has gone up 20 cents a gallon over 10 years, which represents an average increase of 2 cents per gallon per year. Now, that doesn't mean it went up 2% every single, or 2 cents every year. And there could have been years where it went up and years where it went down, but on average, it's been going up 2 cents per year. And for some applications, this is accurate enough. Now, if it's not, we can do something different. But if the interval is not too long, this should be a very good approximation to how much the change is actually taking place. All right, now here's a financial example. Okay, I kind of pulled that one out of the air. If you're not familiar with the stock market, the S&P 500, which stands for it's on the next slide. Standard & Poor's 500 is an index of the prices of the 500 largest stocks in the country. Let's just say that Wall Street pays a lot of attention to this number. And down the road, when you actually have money to invest, you'll be paying attention to what the S&P 500 is doing, because it gives you a sense of how the market is doing overall. Now, let's just say that at the end of each of these 5 years, this is the price of the S&P 500. So the question, of course, is going to be, on average, how much did it change over this time frame? Now, some years it went down, like here, but most of the time, it went down here too, look. So it goes up and it goes down, but we'd like to figure out, on average, how much did it change over this time frame? Okay, well, you can think of this as X1 and X2. You can think of this as f of X1 and f of X2, because the price of the index depends on the time. Or in other words, this value is a function of the time or the year. So we can plug these into our formula. Okay, so this is f of X2. Oh, I see. I don't know why I did this. The question suddenly changed to 2016. I didn't even notice that. That was a little bizarre on my part. So, all right, think of this as X1. This is f of X1. Okay. Okay, whatever. You get the idea. It's a 3-year change now. Okay, so that's f of X2. This is f of X1. X2, X1. So over those 3 years, it went up by about $763.86. And so on average, it's going up about $254.62 per year during this period, that is. Which is not bad. I mean, if you put your money in the S&P 500, you'd be happy because you're making money every year. All right. Now, most of the time, we're not going to deal, well, I shouldn't say most of the time. It depends on what kind of information you have. Here, if you notice, we do not have an actual function. Okay, we do not know, for example, that, let's say that if we did have a function, it might look like this. And that means that X is the year and Y is the S&P 500. If we had an actual function, it would be easy to figure out what the S&P 500 would be during any given year. We don't have that information. We only have the individual numbers. But we can still figure out the average change by doing what we just did, moving from, let's say, here to here. The average change would look something like this. If we do have a function, though, that does make things a little bit simpler. Like here, we'd like to know the average change of this function between the values 3 and 6. Okay, now, in order to get a better view of what we're doing here, why don't we switch to our favorite website, Symbolab, which I don't remember if I showed this to you last week or not, but Symbolab is a very useful website that helps you graph functions and also in some cases solve for them. So I'm going to tell it that I'm interested in the function y equals x squared plus, minus 3x plus 5. And all I want to do is look at the graph. So what I'm interested in is figuring out how much it changes between 3, which is approximately here, and 6, which is way up here somewhere. Okay, so how can we do this? Well, what we're going to do is call this one x1, and this will be x2. And now I've got to calculate f of x1 and f of x2 myself. Okay, in other words, f of x1 is f of 3, and f of x2 is f of 6. That I have to do myself. So these are done on the next slide. Once I have that information, I can go ahead and use my formula. Okay, so f of 3, now we're very familiar with this concept right now. Just plug in 3 for x, and you can see that f of 3 is equal to 5. And then f of 6 is equal to 23. So now we're ready to solve for the whole thing. We're going to calculate the average rate of change for this function over that interval with this formula that we now know very well. So here's the two f's, f of x1, f of x2. These are the original x's. And it turns out that the average rate of change during that interval was 6. So over that time frame, on average, when x went up by 1, y went up by 6. Okay, so for each 1 unit increase in x, y increases by 6. Now, by the way, this works in both directions. If I decrease, I'll add that up here just to make sure it's clear. For each one you decrease in x, y decreases by 6. You have to go in the same direction because the slope is positive. And if x goes up by 2, for example, y goes up by 12. Okay, so that's what this is all about. That was pretty straightforward. Now, we're going to look at something interesting here, determining the changes in a function. Now, imagine we had this cubic function, which we can go look at in Symbolab. I find that their graphs are typically a little clearer than Excel, but Excel does its best. X cubed minus 3x. No, let's try that again. Yes, okay, let's see what that looks like. Ooh, now that's pretty cool. Now you notice we mentioned this once before. Since it's a cubic function, it could potentially have 3 different solutions, which appear to be -2 radical 3, 0, and +2 radical 3. But what we want to know is how to identify where it changes the sign. So this is what Excel shows it as. It's still, you can still see what it's doing. It's maybe not as cool as this, but you can still see the important details. So in other words, over the range from -infinity let's see. This is -2. Now, this is why I like Symbolab. You see what it says here? -2, 16 is the maximum. If you notice within that range, that area, this is sometimes called a local maximum, as we'll discuss later on. In that immediate area, the value of y will not go above 16. So therefore, when x reaches -2, after that, the function starts to turn down. So it rises continuously up to where x equals -2. So we say that the function is increasing from x equals -infinity up to -2. But once we get past -2, it decreases until we reach the bottom here at +2. Okay, so between the range from negative to +2, the function is decreasing. And then from that point on, it continuously increases and it never turns down again. So from 2 to +infinity, the function is increasing. I hope you can see that just from this graph. So that's why the graph is so helpful. It's rising up to -2, falling down to +2, and then it continuously rises forever after that. And those 2 points, we call that a local or relative maximum because there are other values greater than 16, but not in this immediate vicinity. Same thing here. We bottom out here with x is 2, y is -16. There are values of y less than -16, but not in this immediate area. So these are referred to as a relative or local maximum and a relative or local minimum. And by the way, if we find a point which is greater than any other point, we call it a global maximum. And if we find a point that's smaller than any other point, we call it a global minimum. Here, these are relative. This is a relative maximum and a relative minimum. By the way, here's an interesting fun fact. This is English related. The plural of maximum, because this is a Latin word, I just want you to know this in advance. It's not maximums, it's maxima. Same thing is true with minimum. Minimum is singular. It's that, oh, it's that crazy Latin. Singular, to pluralize it, it becomes minima. All right. Also, both maximums, or maxima, I should say, and minima, are referred to collectively as You sometimes hear this word maxima and minima are known as extrema, they're called, where the singular is extremum. Or think of them as extreme points. Okay, so in other words, a maximum obviously means the largest, minimum is the smallest, but extremum could go either way. All right, I just wanted to throw that in there because we're going to run into these words again and again. All right, now, how do we identify? Now, how did we know this? I mean, sure, the graph is helpful, but how do you know that these are the 3 points where the function changes direction? Because if you notice the slopes, look at the slopes, right here at the local maximum, the slope of this function switches from positive to negative. And it continues to be negative until we reach this minimum where the sign switches from negative to positive. So in order to identify these points, one technique we can use is to find points where the sign of x change, I'm sorry, not the sign, the slope changes sign from either positive to negative or negative to positive. Okay, and that's our tip, that this is potentially a global or relative maximum or global or relative minimum. It's the change in sign of the slope that tells us what we need to know. Okay, now, oh, I did have this in here. So look at this one. Well, here I'm just identifying, because we've already seen it on Symbol Lab, that when x is -2, the function reaches a local maximum value of 16. So that makes this our local maximum. The other point down here was to negative 16. This is a local minimum. And as I pointed out, an absolute or global maximum is the largest of all. So in other words, there can be more than one local maxima or maximum or minimum. The largest of all of them is the global maximum, and the smallest of all the minima is the global minimum. Now, we're going to study this in more detail later on. Here we're just introducing this topic. We're going to see that there are other techniques that we could use to find these points that are maybe a little bit quicker, but we're not ready for them just yet. Okay, we have to learn more concepts before we can come back and revisit this. But I want to give you a hint. One more thing that I wanted to point out here is that exactly at this maximum and minimum, the slope of this curve is 0. In other words, I could define a flat line. In fact, let me do it on here. And it's a very crude graph, but you can see at precisely that point, the slope of a tangent line is 0. And that's another clue that this is either a relative maximum or a relative minimum. This is a technique that we do not know how to do just yet, but we will work on that. In the meantime, though, we can continue to use this technique where slope is positive, it goes to negative, and it goes to positive, and that's enough to figure out where these extrema are. Okay, now what's next? Composition. You may remember this from your travels. We can define functions that are themselves functions of other functions. In other words, let's look at this one. This notation simply means add together f of x and g of x. This notation, second one, means f of x minus g of x. So in other words, this is just another way of expressing what happens when we perform algebraic operation on two different functions. Fgx means f of x, g of x. And finally, f divided by g over here means exactly what you think, f of x over g of x. And of course, here we must make sure that this is not equal to 0. And also, now we know why. So you may see this notation as you go along. It means the same thing. Let's see if I've got some examples. Yes, I do. All right. So what we're going to do is start with these two functions, and we're going to perform all of those algebraic operations on them. And you'll see it's pretty straightforward. It's pretty down to earth. Let's start with the addition. Okay, so you know what I'm going to do, just to make sure we don't have to keep scrolling back and forth. Let me just copy these on top of this one. Just a reminder. Okay, you know how annoying it is to have to keep going back and forth. So with those two together, the sum is exactly what you would think. You just have to be careful when you eliminate these parentheses. If there's any negatives, you have to make sure that you apply the negatives to every term within these parentheses. That didn't happen here, though. And we very simply end up with x squared plus x minus 1. All right. Oh, you know what? Let me just do one quick thing here. What is today, the 8th? Hold on one second. Yes, today's the 8th. Okay. No, all right, just want to make sure. All right, so now what about the next one? So I'm going to copy this into the next slide. This is subtraction. Now, like I said, you have to watch it. In fact, I probably should have done this in 2 steps. This equals x minus 2 minus x squared oh, I forgot, minus 1. With PowerPoint, exponents are not that simple to do. Let me just get this going here. All right, and then you can see where that last step comes from. We consolidated the 2 constants, and we end up with this result on the bottom here. Very good. All right, that was pretty straightforward. But again, the negative out here has to be applied to both x squared and 1. Now, how about multiplication? Well, it's not that hard, but now, see, now this time we got kind of lucky. We were able to use FOIL. In fact, why don't I pencil in these FOIL results just so you can make sure you get it. F is x cubed. O is x. I is negative 2x squared, and L is negative 2. Now, it appears that none of these can be consolidated, but just as a rule of thumb, just to keep things neat and simple, when you have an expression like this, we try to list them in descending order of their exponents, okay? In other words, x cubed comes first, x squared is second, x is third, and the constants are last. There's nothing wrong with this one, but by convention, we usually try to arrange these terms so that the highest exponents come first and the constants are last. And this is, of course, a cubic equation. In general, I mean, we'll see later on, this is a special kind of polynomial, it's called, of degree 3, meaning that it has an x cubed in it, which is the same thing as a cubic equation. All right, and then we have division to deal with. All right, well, there's not much you can do with this one. I mean, really, you've got x minus 2 over x squared plus 1. It's, what can you do with it? Nothing really. Sometimes you can, though, all right, but not so much here, so you just leave it alone. All right. Now, this is something that maybe you've seen this before, maybe you haven't. This is something that is unique to functions. We're going to create what are called composite functions. And the way it's written now, these both, of course, mean the same thing. F now becomes a function of g. Down here, g is a function of x. How do you solve for these? How do you evaluate these? Well, it's not as difficult as it looks. They're known as composite functions because they are functions of functions. Okay, so that sounds very complex. Functions of functions. So let me show you some examples. And when you see them, you'll say, oh, okay, that's not as bad as I feared. So let's use these two again. To do f of g, which remember is simply shorthand for f of g of x. And this second one is g of f of x. Okay, so what's going on here? All right, let's go to the next slide, and I've got everything written here one more time. So here's what you have to think of. f of x is x minus 2. That implies that f of g of x means I'm taking every x and replacing it with g of x. It's no different when you think about it than f of 3. You're replacing all the x's with 3's. Now you're replacing the x's with g of x. So therefore, oh, here it is right here. That's the key to the whole thing right there. This x was replaced with g of x. And since g of x is x squared plus 1, I literally just substitute it here, reduce it, and this is my final answer. Okay, so in other words, it looks like a nightmare, but in reality, it's no different than what we were doing earlier, except that now the x's are being replaced with another function instead of a constant. And then you have to evaluate it from there. All right, so now let's do the opposite, g of f of x. And they're not likely to be the same, by the way. So now this one, g of x, x squared plus 1, g of f of x is going to take, we're going to take our x's and replace them with f of x. Okay, so here we see it down here, that x squared became f of x squared, and f of x itself is simply x minus 2. So x minus 2 squared plus 1. And here we have an opportunity to do a FOIL. Okay. I think we all enjoy FOIL. It's so nice and simple. Okay, and then O is here. All right, so we consolidate these into x squared minus 4x plus 4. And that's what we see down here. We also have that 1 at the end, and we consolidate, and we're done. So it's a fairly straightforward extension of what we were doing earlier with constants. But it opens up a lot of possibilities now. Okay. So it's important. But again, once you recognize that it's a very similar process, it shouldn't be too difficult. Very good. Now, what if I need an exact value, though? What do I do now? So the next step is to figure out how to evaluate these composite functions with a specific number. So typically, the quickest thing to do is to evaluate what I'm calling the inside function. In other words, this, the g of x in this case is the so-called inside function. So in other words, what you should do is don't put g of x into f of x, calculate what g of x is, come up with a constant, and then evaluate f of that constant. Okay, and then yes, this f is the so-called outside function, as it's called. Oh, oops. Oh no. All right, don't you worry. Whoever's not getting it, as soon as we do some examples, it'll all become crystal clear. This, by the way, that reminds me, let's look at what's going on with this week's problem sets. I want to remind myself what, okay, now I can't find, oh, here it is, here it is. Practice problems number 2. Oh, this is domains and ranges. This is average rates of changes here you're doing the simple operations. You're adding them, you're subtracting, you're dividing, and you're multiplying. Okay, you should have zero problems here. Okay, remember with the domains, just avoid numbers that give you division by zero or the square root of a negative number. Okay, now it's number 3 that I wanted to really look at. Oh, no. These are not what I wanted to see. I may have to make up another one. Now that I'm looking at these, I was hoping to see a bunch of composite functions. Oh, all right, I'll tell you what. Oh, maybe there was a 4th one and I never posted it. Hold on one second. Oh, because I really think that if you could just practice with this just a little bit, you'd be all set. No, all right. Well, I'll write a new one then. Because I think really you'll find this to be very straightforward. In fact, I'll tell you what we can do. Why don't I make one up right now and see what you can do with it? All right, let's try this. Because the great thing about a class like this is that if you just practice enough, you should be able to do anything. All right, I'll tell you what, let me make one up right here and now. F of x is x minus 4. G of x is x squared. Oh boy, hold on. Plus 1, okay? Now, I don't think we need a ton of practice with the basic operations. I mean, I certainly am going to put a question set for you together that requires this. I'll create a 4th problem set tonight, I guess. I'll post it on Blackboard. I'm sorry, Moodle. But the one I think you do need practice with is the composite functions. So I'll tell you what. Let's do this one together. All right. So how would you find f of g of x? Okay, what should I do? All right, go ahead, Fernando.
Would you need to like take the equation for g and combine it with f, like the x within the
Yes.
formula?
Yes. So in other words, I'll have g of x minus 4. So again, I'd remind you that if I asked you for f of 3, I would have put in 3 minus 4. Instead, the x is being replaced with g of x. And now this is equal, as you know, x squared plus 1. And now you combine these and you're done. So let's try the other case. Let's try g of f of x. What I'm going to do is replace the x squared, not with a constant, but with f of x. So then I'll end up with x minus 4 squared plus 1. And if you want to do a quick FOIL here, that's x squared. The outer is minus 4x. The inner is minus 4x. The last is 16. So this equals x squared minus 8x plus 16. So now all of this will be replaced with x squared minus 8x plus 16 plus 1. And that's easy to combine them because it's now just x squared minus 8x plus 17. All right, so again, you can see it's very much like we did in the first problem set, except the constants are being replaced with other functions. So let's do another one, except this time I'm not going to tell you the answer. All right, let me think of another one. Let's try, I'll try to avoid any that are horribly complicated. All right, that'll do. All right, so you're going to find f of g of x and g of f of x. All right, so there's no squares here, so this one will be extra simple. So why don't you take a second, get out a piece of paper, and see what you can come up with. Oh, somebody's already got it. Oh my God. Oh, did I overlook it? Okay, I hope that you're right, because I was a little surprised. Let me see, did I just zoom right past it? Oh, you know why? Because I didn't scroll down far enough. Oh, okay. All right. I take back what I said before. I didn't even notice that they were down there. So there are some cases here that you can work on. That's good. We definitely need the practice. Thank you for pointing that out to me. Like I said, I mean, I was stopped here and I said, oh my God, what did I do? Did I forget? Here we are. I knew something was wrong. Okay. All right, that's good. All right, perfect. Perfect. Okay, so in the meantime, let's see how we did here. Now, I don't know what the answers are either because I just made these up on the spot, but let me just copy these to the next slide. All right. There's a hint for the first one. So remember, just take x and replace it with g of x. All right, and if you do that, what's your answer? Okay, now watch this. Oh, by the way, does anybody have an answer? Oh, you know what? I just realized it's going to be tough to type an answer into that chat box when we're dealing with math. All right, I'll just do it right here. Now remember, here you're going to multiply the 3 by both of these numbers, and you're just going to wind up with 3x plus 20. Okay, I hope did everyone get that one? If not, let's figure out why. All right, did anybody not get this? All right, I'll take that to mean everybody's got it. All right, that's good. And then when we do g of f of x, and again, let me just copy that in here. We're working this backwards, basically. So g of f of x means that you're taking all the x's and replacing them with f of x. That's the key right here. If you get this part right, you're all set. The rest is essentially just algebra, substitution, and some basic algebra. So that is the challenge, this piece. Okay, so I'll make a little note here. Replace each x in g of x with f of x. Okay, that's what you're doing here. And then I might as well add that back here. Replace each x in f of x with g of x before you carry on. Okay. Nice. Oops. Okay. And then, of course, you probably should continue. You know, don't leave it like this. If it can be simplified, you should always simplify it whenever possible. All right. So did everybody get that one too? All right. If not, we'll go through it again when we go through the second problem set next week. All right. Now, as I started to say, this may not be what we want. We may still need a specific result. So we're going to now learn how to evaluate these at a specific value of X. So let me show you an example, because I think you'll realize pretty quickly that this isn't really that difficult. Let's say, for example, you were told that f of X is X plus 7 and g of X is 2X squared minus 3, but I don't want to know f of g of X, although I need that to get to my answer, but I'm really interested in knowing f of g of 1. So we're going to think of this as my f is the outside and g is the inside. So we're going to evaluate the inside function g of 1. Okay, so if I do that, we already know how to do this. If g of X is 2X squared minus 3, g of 1 must be 2 times 1 squared minus 3 negative 1. And so look how simple this becomes. All of a sudden, this tells me that f of g of 1 is equal to f of negative 1. And that we definitely know how to do. We found earlier that that's easy. So since f of X is X plus 7, f of negative 1 must be negative 1 plus 7, which equals 6. And I'm done. Look how easy that was. All right, now this is written out in the next slide in maybe a little bit cleaner detail. Let me just show it to you here. G of X is here. Here's g of f of X. Now, we're looking for f of g of 1. So we start by solving for g of 1, and you can see the X became a 1. All right. And now f of g of 1 is nothing but f of negative 1. So the X becomes negative 1, and my final answer is 6. All right, so was that difficult? No, but you had to know what you're supposed to do. The key to the whole thing is to solve this first and then evaluate. We'll say this is step 1. Step 2, evaluate. Okay. So if you follow this example, all the rest of them are exactly the same. You should have no trouble at all with that. Now, what I'd like to do here, although it's in the slides, but I would like to challenge you to do this next one without looking at the answer. So in other words, let me just add another slide here. Given that, once again, f of X is X plus 7. G of X is X 2X squared minus 3. We've already solved for f of g of 1. We discovered that it was equal to negative 1. Let's try this. Let's try g of f of 1. All right, so I'm going to see if you can do this. I'll give you a couple of minutes. Try this out and see what you come up with. If you can do this one, you can do all of them. All right, so that it won't be a problem ever again. If not, we'll go over it again in great detail next week when we cover the second problem set from chapter 1. Now, I don't have a prize to give you if you for the first one with the correct answer, but let's pretend that there is a prize. All right, now I don't know the answer either. So let's see, what would you do? So let's start with f of 1. 1 plus 7. And remember, all we're doing is replacing all the x's in f of x with a 1. So therefore, g of f of 1 is nothing but g of 8. So therefore, go back to g and just replace all the x's with 8's. Okay. So 8 squared, of course, is 64. And 128 minus 3. Yes, exactly. We have a winner. Dal Elizabeth. You got the prize. The prize is that everybody knows that you got the answer right. Okay. It's a pride thing. All right. There's no gold medal here, but this is a very good prize. Okay. So does everyone think that they understand this? Okay. All right. I'll assume that that means yes. Now, to my great shock, it's almost 10 o'clock already. Now, you know that we need a break in this class because it's so long. So I think this is roughly where we stop. You are getting it. Okay. It's just a question of doing a few more. You know what? I'll tell you what, before we have our break, let's just do one more and then we'll have our break because I want to make sure that everybody gets it. All right. So f of x, let's say, is x squared plus 1. G of x is 2x minus 9. And I'm gonna give you two of these. F of g of 1, g of f of 0. Ooh, there's two of them. All right. So why don't you take a minute and see what you can do. If you can get this one too, I think we're in pretty solid shape. Okay. So always remember, the first thing you do is evaluate this so-called interior function. Always that comes first. All right, so I'm going to start helping you here. So the g of 1 is -7. Therefore, f of g of 1 is f of -7. Aha, we have some answers. Okay, -5. Let's see. -7 squared plus 1 is 49. Oh, do you mean for the first one or the second one? All right. So did you do g of 1? G of 1 is 9. -7, I'm sorry, it's -7. And then when you put that back into f of x, you have -7 squared plus 1, which is 50. Okay, try it again. Just go back and look at your results. Now the second one, remember it's g of f of 0. So start by calculating f of 0, which is 0 squared plus 1 equals 1. And that means that in the second case, g of f of 0 is g of 1. And that means you've got 2 times 1 minus, oh, well, what do you know? Just by coincidence, it's -7. Let's see. Let me make sure we did that correctly. F of 0 is 1. Therefore, g of f of 0 is g of 1, which is -7. Okay. So, all right. So if you did not get this right, why don't you take a look and let's see what happened. Okay, what we want to do is figure out what exactly went wrong. Okay. So first things first, did we do g of 1 correctly? All right, so what happened? When you plugged in 1 for x, well, let's do it together right now. G of 1 means 2 times 1 minus 9, okay, because g of x is 2x minus 9. The 1 replaces the x, and you end up with -7. Make sure, if you don't have that part right, the rest is just not going to work. So make sure that one is working. So everybody who did not get, oh, okay, yeah, Wi-Fi, technology is just not as reliable as people seem to think it is, especially cell phones. No, especially email. They're both bad. Okay, they let you always down at the worst possible moment. Have you ever noticed that every time you get an important phone call on your cell phone, what ultimately happens? Okay, so Dallas Beth, you got what the answers correctly now? Okay, good. So this has to come first. Once you have that, the part you're actually looking for, f of g of 1, think of it now not as f of g of 1, but f of -7, which means come back up here and replace all x's with -7. Okay. Whereas on the right-hand side, g of f of 0, start by evaluating f of 0. All the x's become 0. So here we end up with a 1. So now what you're actually doing when you're evaluating g of f of 0 is you're evaluating g of 1. So you come up here and you replace the x with a 1, and you should end up with -7. Now, if this is still not happening, we can have a Zoom conference between the people who need it and just go over this a few more times until you get it straight. We're not going to abandon you. If you're still not getting it, we can still have what amounts to office hours. Okay. I mean, yes, we're not here in person, but we can have Zoom office hours. All right. So if it's still not clear, that's all right. Just write me an email and we'll make an appointment. Okay. Not a problem. And I'll make up plenty of examples. And when we're done, you will be an expert in this area. Okay. Because most likely there's one little thing that's tripping you up and we have to figure out what it is. So anyone who wants to do a Zoom session, just send me an email. We'll figure it out. It's just going to come down to when is it mutually convenient for us. It's easy to set it up. It's just a question of making sure we're both free. So, all right, just let me know. Don't worry. Just send me an email and say, I need a Zoom session to go over this again. And we'll take care of it. Okay. Very good. All right. So anyway, so now, yes, now we can really have a break. And so we'll have a quick break. Last time, I think we did 15 minutes. That sounds about right. Roughly 15 minutes, just enough time to get some refreshments and clear your head. And then we'll carry on. We're almost done with chapter 1. I'd like to be completely done with it today and then at least start chapter 2, which I forget exactly what's in chapter. Oh, linear functions should be next. Let's see. One is functions, just generic functions. Yeah, linear functions. This proves to be actually extremely important in practice because the majority of the functions you'll see in the real world, many of them, I should say, are linear functions, which you're already very comfortable with, by the way. So this chapter 2 actually might be easier than chapter 1. Of course, we want to get to it. All right, so let's knock it off. We'll come back around quarter after, let's say 20 after 10. We'll come back here and we'll wrap up this first chapter, which just has 1 or 2 more topics, and then we'll start our linear functions, which should be very, very familiar to you. Okay, and that's always nice. All right, so I'll see you in a bit. All right, so it looks like we're ready to go again. So we're almost done with this chapter. There's one more thing we want to look at with composite functions. Basically, okay, two more topics here. We want to figure out how to determine the, oh God, I lost my place. The domain of a composite function. Okay, this is a little bit trickier than what we did before because we have to figure out what the function itself is. So let's just say, if you look at this one carefully, you'll see that g of x, well, let's put it in here. The domain, in this case, is all the reals except for one. Okay, so if you use this in set theory notation, you recall the way we wrote these. The union means we're combining these two sets. This is, if you look at the real number line, you might recall the way that we typically express this was that we would have a whole at one, and all the rest would be filled in. In other words, what this is supposed to show you is it's all real numbers except for one. And so what's happening here is that you remember this round parenthesis indicates that we're not including the one. So basically, this is just another way of saying all real numbers except one. And down here, you can see we have a similar potential problem. If x equals 2/3, then you'll have division by 0. Okay, because 3x minus 2, when you evaluate x at 2/3, you'll get 2 minus 2, which is 0. So here we have to avoid 2/3. So the domain is written in a very similar way. In other words, this very complicated looking notation simply means all real numbers except 2/3. Actually, what I should have said is except x equals 2/3. It's not the y that's the problem, it's the x. The x cannot be 2/3. Now, by the way, as long as we're thinking about this, why don't we go back to Symbol Lab for a minute so you can visually see why this is happening. I mean, sure, we're getting division by 0, but we want to see what this picture looks like. I think it'll gain more insight into what we're doing. So the first one, whoops, 5 over x minus 1. All right, let's check this out. So you can see this red vertical line is x equals 1. We cannot substitute x equals 1 into this function. So this is an asymptote for the function. Now, it turns out that you also cannot substitute any value of x into this function and end up with a 0. So as far as the range is concerned, we cannot have 0 in our range. Okay, but as far as the domain goes, the only number that's missing is 1. And that's, again, because of division by 0. What about the other one? 4 over 3x minus 2. Oops. Oh, whoops. This thing is not reacting the way I'm expecting it to. There it is. All right, let's look at this. And we should see that there's a vertical asymptote at x equals 2/3, which means we cannot substitute 2/3 into this function. And there it is, 2/3. All right. And once again, which is usually the case with ratios like that, the range excludes 0 as well. Okay, but here we're only interested in the domain. So what does that mean then when we try to combine? Well, let's see what's going to happen. All right, so first of all, let's figure out the value of f of g of x. All right, so first let's do that. So if f of x is 5 over x minus 1, and g of x is 4 over 3x minus 2, f of g of x would mean you have 5 over g of x minus 1. Now this one's going to be a little tricky because we've got a ratio in the denominator. Wow, what do we do now? Well, our strategy is to rewrite this 1 in such a way that we can consolidate these two terms. And so our best bet is probably to simply write it as 3x minus 2 over 3x minus 2. Why did I choose that particular version of 1? Because you can see, first of all, it is 1. And secondly, they both now have a common denominator. So what I can do now is write this as now we have to watch it because there's a negative sign here, which applies to this entire expression. And now, wow, this is a mess. Let's go to the next page. So I'll put this back here again so we can review it. 5 over, oh, what happened here? I was trying to get your, okay, go ahead, Fernando.
So I have a question for when you for the last slide when you did when you put 3x minus 2 on both on the other side, wouldn't that like cancel out or something like that?
Yes, exactly. Yes, but it's a more convenient form than just 1. In other words, yes, that's true. You're absolutely right. It was chosen that way on purpose. In other words, it's supposed to cancel out, but it's more convenient. Let me just throw another example here real fast to remind you, so you can see the parallels with what I'm doing here. Let's see, for some reason, it gets like this sometimes. My screen won't show my icons. There they are. Geez, why does that happen? All right, just a quick reminder. Imagine you had something like this going on. 3/7. Hold on 1 second. 3/7 minus 1. What would you do with that one? We don't want to leave it like that. It's messy. We like to simplify whenever we can. So what you can do is rewrite this as 3/7 minus 7/7, with the understanding that these do in fact cancel out. But look what you can do now. Now you can create one ratio instead of having these two terms. So in other words, you're choosing a more convenient form of 1 just to make sure that you can combine them into one nice ratio. Now, there's nothing wrong with this. It's just that it's usually in math, we usually like to simplify everything. And one way to do that is to rewrite numbers, or not necessarily just numbers, any expression in a more convenient format. And that more convenient format means we have a common denominator of 7. So that was the logic behind, that was the method behind my madness here. I want to have 3x minus 2 in the denominator of the second term, because now I can consolidate them. And in fact, that's exactly what happened here. Now, you'll see in a minute, you might not think so, but this will make things easier for us. So let me just quickly copy that down again. We have 5 over 4 minus 3x minus 2, all divided by 3x minus 2. So what I want to do is evaluate this numerator in the down here as 4 minus 3x plus 2 over 3x minus 2. Now let's simplify that. So I can consolidate these two. Now it appears that we still have a mess on our hands. but not really. Watch, let me show you another case that will come in handy here. Suppose you had something like this going on. All right, let me do a new page. Suppose you end up with something like this. What if I had something like 2/3 divided by 3/4? Now, what this means is that I can rewrite this algebraically as 2/3 times the inverse of this ratio. And so now I end up with 8/9. Or if I have something like this, I can rewrite this as 7 times 2/5, where it's understood that 7 is the same as 7/1. And now I can write this as 14/5. So this is an interesting result, because now this catastrophe turns into something pretty nice. So I want to do something like that here. I'm going to rewrite this as 5 times the inverse of this expression and with the understanding that 5 is implicitly 5/1. So in the numerator, I have 5 times 3x minus 2. Down here, I have 6 minus 3x. And ultimately, I wind up with 15x minus 10 over 6 minus 3x. Now, what does that get us? Well, you can see that f of g of x, which is what this is, cannot allow x equal to 2. Because if I do have a 2 in here, I'll end up with division by 0. So the domain of this f of x, g of x, is all the reals except for 2. Okay, so 2 is disallowed in this composite function because that would lead to division by 0. Now, guess what? All of this work wasn't absolutely necessary. I'll tell you why. Because we saw earlier that f of x cannot allow for 1. X cannot be 1. Okay, so let me consolidate all of these. You can see what I'm doing. We know that f of x cannot have a x1 in its domain. Therefore, what that means is that since f of x 1 is not in the domain of f of x equals 5 over x minus 1. That means it cannot be any value of x at which g of x equals 1 is not in the domain of f of g of x. Okay, in other words, what we're saying here is that this is f of x. F of g of x would also have the same restriction. Okay, so you can see g of x must not equal 1. But, so now this time we're not talking about x, we're talking about g of x. So if g of x cannot equal 1, what we're going to do here is figure out what value of x causes this to happen. So we're going to set 1 equal to 4 over 3x minus 2. I'm going to cross multiply. Remember, we started out with 1 equals 4 over 3x minus 2. cross multiply to get this. And what we discovered is that g of 2 equals 1, which is not allowed. So therefore, 1 is not in the domain of f of x, implies that 2 is not in the domain of f of g of x. Now, the way I just did it here, you don't have to follow that approach. You see what I did up here? I did it the long way. And she said, listen, let's figure out what f of g of x is in the first place. And it should be clear then what the domain is, okay? So therefore, you can see I did it this way. This is the long way, but you know what? It might be the more straightforward way. By actually knowing what f of g of x is, it should be clear that we cannot allow for x equals 2. But this is sort of like an indirect approach. By knowing that f of x can't have a value of 1 for x, we can figure out what the appropriate value would be for f of g of x, which turned out to be 2. So you can use either approach to find out what values do and do not belong in your composite function. All right, so now here's another skill that might come in handy. What if you have a composite function and you want to break it up into the individual functions? Okay, in other words, let's just say that we have f of x is radical x minus 8. Or actually, what we can do is this. Suppose that it turns out that f of x, oh, I'm sorry, I missed that. How so? What part are you referring to? No, 2 is the answer. Yes, it is. 2 is the answer. In other words, what value must we not allow for would be 2. Okay. All right. Anyway, so let's just say this turns out to be a composite function. So we're going to be careful. I have to be careful with the letters this time. By the way, you can define any number of functions you want. It doesn't have to be f. Sometimes we see f, sometimes it's g, sometimes it's h. So you can see here, this f of x is itself the result of 2 other functions, g of x and h of x. And what we want to do is figure out what they are. Now, since f of x was radical x minus 8, if these are the original functions, you can see g of h of x would be radical x minus 8. Okay, because what's happening is that h of x is being replaced or substituted for that x. So that means that we kind of figured out that this f of x is a composite function consisting of g of x is radical x, h of x is x minus 8. Now, do we ever really need to do this? It's possible. It depends. But what the purpose of this is just to show you that it can be done. Okay, in other words, you can take a composite function and break it up into its individual functions under some conditions. Sometimes it's not really feasible, but you just need to be aware that it can be done under most conditions. We're not going to ask you to do this. Okay, this is too much, but just be aware that this is a possibility. Oh, and I see here we've got a refresher for absolute value. Now this is easy because you've done this before. Suppose you have this as your function. I want to know, now remember, oh, by the way, why don't we throw this into Symbol Lab so you can figure out what this is all about. So it's absolute 4x plus 1 minus 7. All right, I want to see what this thing looks like. Now, when we say the solutions, if we're looking for the solutions of this function, we're of course asking for the points where the function crosses the horizontal axis. So this intercept, as you can see, is -2, 0, and this one is 3/2, 0. So the two solutions, we already know now by cheating a little and looking at a graph, are -2 and 3/2. But why don't we do this algebraically? Ah, very interesting. So here's what we'd like to do. We will set this equal to 0. Now, here's what we have. Now, what do we do with this? 4x plus 1 absolute value equals 7. Keep in mind that the absolute value of x is x if x is positive or non-negative, and negative x if x is negative. This is the formal definition of absolute value. That means we have two solutions here. So we're going to take, this is x. Okay, this is negative x. If we think of x as being okay, so I'm writing it out in the same terms. I shouldn't probably write it like this. Negative f of x. Let's put it this way. In fact, I'll tell you what. Let me rewrite this. Just in the most general possible terms, the absolute value of f of x is either f of x itself, if f of x is positive, strictly non-negative, and negative f of x if it's negative. Okay. Now, that means we can think of this as, because the original function was 4x plus 1, this is f of x, this is negative f of x. We set them both equal to 7, and we solve for them. And you can see here, we can rewrite this as 3/2 and -2. And so just as the graph pointed out to us, the solutions are in fact -2 and +3/2. So this was the part that was going to be tricky. There's two solutions to an absolute value function. All right, and so that's what this is all about. If this was f of x, this is negative f of x. Okay, so let's do another one of these. So I'll show it to you on the graph. Absolute value of 2x minus 5 equals 3 or plus 3. So we'll take a look at it. And let's see, right here, you can see, oh, now this is awkward. Wait a minute, did I do that right? Absolute 2x minus 5 plus 3. Oh, I don't know, something may have gone wrong here. Oops, there might be a mistake here. Hold on. Oh, I hope not. Absolute 2x minus 5 plus 3. Oh, okay. You know what? This example is not correct. Oh boy. I'll have to post an updated version of this. You know what happened? There's an algebraic error here. So this example, oh, I hate when this happens, is not correct. So I'll have to make up a new one. Sorry, this one is not right. Let's do a new one. Let's start a completely new one. How about this one? Let's try for the function f of x equals absolute 2x minus 7 plus 2. And that means, i.e., what are the solutions of this function? All right, now, before we go any further, let's make sure that I didn't goof this one up. No, it's still wrong. All right, you know what we need to do? Let's change this to -5. There we go, perfect. All right, let me fix that. Now we're good. All right, so how do we figure this out? Now, the symbol lab will tell us what we need to know. So what we do first is we typically set this equal to 0. So in other words, 0 equals absolute 2x minus 7 minus 5. 5 equals absolute 2x minus 7. So this is the tricky part. That implies that 5 equals 2x minus 7 and 5 equals negative 2x minus 7. So over here we have 12 equals 2x. Over here we have, oh, well, I'll tell you, let's get rid of that, those parentheses, minus 2x plus 12. Okay, so that means here, minus 7 equals minus 2x. So we have 6 is x and 7 halves equals x. All right, so let's confirm that with the symbol lab. Oh, no, something's not right. All right, let's see what the problem is. 2x, did I type that right? 2x minus 7 minus 5. Okay, we add that to both sides. No, here's the problem right here. This is supposed to be a 7. All right, that's better. And then when you subtract that from both sides, there we go. That's perfect. All right, sorry, that was a typo. All right, so yeah, we're good now. It's 1 and 6. All right, let's just confirm that. 1 and 6, perfect. All right, so I made a dumb algebraic error right here. This is supposed to be minus 2x plus 7. That's equal to 5. I subtract 7 from both sides. Minus 2 equals minus 2x. X equals 1. All right, so we're golden now. All right, so this is what it's supposed to look like. This one, I will delete it from the notes. I'll send out an updated version. So just remember, this one is not correct, but this one is fine. And now we're going to do something that's kind of challenging, but kind of important. It's this notion of inverse functions. So what does that actually mean? Well, let me show you an example of what that, for example, Think of these, by the way, inverses are functions that essentially offset each other. So you can make the case that radical x and x squared are inverses of each other. So if you were, for example, to take radical 4 and then square it again, you would get 2 squared, which is 4. And if you were to take 4 squared and then take the square root of that, you'd also end up with 4. So like I said, I mean, think of these as inverses of each other in the sense that if you apply both of these to a value like 4, you'll end up with 4 again. It's kind of like maybe, remember this from trigonometry class. If you take the cosine, let's say of 90, and apply the arc cosine. Oh, remember those days? Oh yeah. It was written as -1. So the cosine and the arc cosine are inverses of each other. Anyway, so it should be possible in principle to do this with any function we choose. And we're going to show how to prove that we've done it correctly, but let's just do an example first. So, oh, this is the one I was just talking about, x squared and square root of x. The bottom line here is that you know you've done it correctly if both f of g of x and g of f of x give you back x. That's how you know that these functions are inverses of each other. Okay, so, I mean, intuitively, it should be clear that these are just essentially offsetting each other. But here's how we can formally prove it. So no matter what you started with, if you take the square and then the square root, you'll come back to x. Or if you do the square root of x and then square the result, you'll end up with x. Okay, so in other words, this means that this equals x and this equals x. That's how you know that they're inverses. This is an important idea. You'd be surprised how often this will show up. The concept of an inverse. All right, so here's a couple more examples. What about these two? Are they inverses? Multiply by 4 and then divide by 4, are they inverses? Well, according to what I'm seeing here, they are, because f of g of x would be f of, now remember here, this x would be replaced with this. So it's f of, sorry, let me write it like this. 4 times g of x, which is 4 times 0.25x, which is x. And then in turn, g of f of x would be 0.25 f of x, 0.25 times 4x, or x. So that's correct. These are inverses of each other. Now, I don't know if Symbolab is capable of doing 2 functions at a time. Let me just check this out. That would be helpful. If y equals 4x, geez, I don't know. I'd love to be able to show them both to you on the same graph, so you can see how they're related to each other. I just don't know if that works on here. There's y equals 4x. Geez, you know what? Let me see if I can do some research on Google. Well, all right, we don't have that much time to waste with this. I'll look into this later on. I guess it's capable of doing it. All right, well, let's try it here. Oh, I may have accidentally stumbled onto it. Oh, all right, here we go. Well, you get, I don't know if this is helping or not, but this is what they look like. But all right, anyway, so let's do another one. Now, in general, how do we do this? In other words, here all we were asked to do is prove whether they are or are not inverses. This didn't tell us how did we find this in the first place. So here's what you have to do. You start out with this function. Now, we want to know what is the inverse of this function. So, of course, we'll write it out as y equals x plus 1 over x plus 2. Now, this is the interesting part. We're going to solve for x. Okay, so cross multiply. And now, of course, I'm going to wind up with a bit of a mess. My goal is to solve for x. Okay, so I'm going to factor out a y. I'll divide out the y from both sides. And now I'm going to subtract. And now here's where it gets strange. I can now rewrite this and this is my inverse. Now, what I want to remind you, maybe I shouldn't have written it. Hold on 1 second. Let's see. I want to make sure I'm doing this right. The notation now, what we're supposed to write here, the first function we can write it as f of x. The inverse is formally written as f inverse of x. So yes, I found the solution, but you should ideally express this as f inverse. This means f inverse of x. And this is, of course, f of x. So basically, you start by writing your equation as y equals that value. You solve for x. And then you swap the x and the y, and you're done. That's what we're doing here. It seems very bizarre, but it works. But formally, they should be written like this. Now, we can prove that they are inverses by using that technique we saw earlier. And what was that again? Oh, yeah. So remember, what we are claiming is that f of x, yeah, here it is. This is our f of x. This is our inverse. If we can prove that this, now look at this thing. This is even more involved than f of g of x. Although it's a similar idea, it's just that now instead of f and g, we have f and its own inverse, but it's the same logic. So f inverse of f of x in this case would be, we take this 1 over f of x minus 2. Because what I'm doing is I'm replacing this x with f of x. Then I replace the value. Now, this is not good enough. I want to prove that this equals x. So watch what I'm going to do. I'm going to multiply this by 1, but a special form of 1. Actually, no, I'm not even going to do it. I'm going to do it like this. I now have a common denominator. Okay. And then I have now 1 minus 2x minus 2 over x plus 2. Let's see. No, sorry, I messed it up. Sorry, this is 1 minus 2x minus 4. Okay, something's not right. F of x, it's all done right here. Let me just jump ahead to where I actually did it correctly down here. This is, remember, f of x is 1 over x plus 2. F inverse of x. Actually, you know what? Let's do this. The inverse is 1 over x minus 2, but why don't we simplify it right here? That'll probably save us some grief. 1 over x minus 2x over x. I think that would be easier to work with than this. So let's make a note of that. 1 minus 2x over x. So therefore, this expression, which is just shorthand for this, means I'm taking the f inverse. Okay. Well, you know what I must have done here? This is, I left it in this form. All right, we'll stick with that. That's fine. This now becomes replaced with f inverse of x. And then algebraically, this reduces to x. Now, I guess I kind of left out an intermediate step here. Let's take a side note here and see why this is true. Let's move this onto a document. Yeah, I just want to go back and prove why this is happening, just because it's a bit messy. Okay, so what you would do now, I did say before, if you have an expression like this, 1 over, let's say 3/4, it's the same as 1 times 4/3 or 4/3. So therefore, if you have 1 over x plus 2, this is the same as 1 times x plus 2 over 1. Okay, which I could rewrite as 1 over 1 times x plus 2 over 1. It's just x plus 2. So in other words, all of this is just x plus 2. And that one is done. Okay, so that is what we were hoping for, but we have to do this twice. Now we have to prove the same thing for f of f inverse. Yeah. So remember, f of x was 1 over x plus 2. So now I'm going to take f of f inverse would be 1 over f inverse plus 2. And that means I've got this expression plus 2. And this is 1 over x, which is x. Okay, so we're golden. Now, this one we're going to need to do a lot of practicing with. You can see this is a little bit messier. But if we understand the composite functions we did earlier, this shouldn't be that difficult. There's really just like one extra step, basically. So, yeah, this turned out to be a mess. I don't know what happened here. Just get rid of it. All right. Anyway, so don't you worry. We'll get tons of practice with all these concepts. I know there's a lot of concepts flying across the screen here, but we'll get plenty of practice with every single one of them. And you can see they do all tie together because now look what we're proposing to do, finding the domain and range of inverse functions. Well, this is very straightforward because it turns out that we have two very important results here. The range of f of x is the domain of its inverse. And the domain, you do not need to know this by heart. It's all about doing techniques. In other words, if I write down on a test, what is the inverse of this function? All you have to do is work out the steps and come up with it. You're not really memorizing anything as such, okay? What instead will happen is we'll just keep using the same concepts over and over again in different applications, okay? So it's not the case that this stuff will suddenly get 10 times harder. Instead, we'll just keep seeing it over and over again with different applications. I know there's a lot going on here. Don't you worry. Once you've done the two problem sets, that'll help bring it down to earth. And then if it's not enough, we'll have some Zoom sessions. Okay. Yes, I get it. It's a lot. I mean, it's not ideal to have this class only meet once a week, but this is the only time it works for everyone. So don't worry. The practice problems will make it hopefully all work better. And if not, like I said, that's why we can have Zoom sessions. All right. Anyway, so here's the results here are very interesting. The range of a function is the domain of its inverse, and the domain of the function is the range of its inverse. Well, that couldn't be more convenient. So look at this one. Now here we're just taking this for granted, but we've already discussed this one. So what is the domain? Well, you can't have a negative square root in the real number system. So therefore, the domain of this inverse is, as it says here, 0 up to infinity, including infinity, which implies that the range is also 0 to infinity. I mean, it should make sense because no matter what number we square, the smallest value can be is x, 0 rather. So I hope you can see why this has to be true. And then we can also claim the range of this inverse, meaning what can come out of this function, because f inverse of x is radical x. If you look at this function on the graph, remember what the range means. That's all the y values that it can assume. This would be its range. In other words, it can't be negative, and so we end up with a range of this, and therefore the original function's domain is also 0 to. So remember, because this was x squared, it stands to reason that the domain oh yeah, okay, the domain let's see, now I've got it. Where did I lost my place? Would have to be 0, infinity. All right. So, all right. No, that was it for chapter 1. All right. So we're done with this. Now, I did mention earlier that I really think the second chapter will actually be more straightforward than the first because it's all linear functions, which are all intimately familiar with, whether you realize it or not, because all we're talking about here is straight lines. Okay. So like, for example, who could possibly forget this equation? Nobody. Y equals mx plus b. This is something that's stitched into your brain cells. It's something you'll never forget. And so you might recall that m is the slope and b is the intercept. So in fact, just as a quick example, suppose that we go to Symbolab and we look at, no, not there. Let's just make one up. How about y equals 3x plus 9? So that implies that the slope is 3 and the vertical intercept is 9. So let's take a look at that graph. So yes, there's the intercept. That's where it crosses the vertical axis. X is 0, y is 9. The slope is 3. It's quite steep. And that means that every time x goes up by 1, y goes up by 3. Forever. It never changes. So this is a linear function. And of course, the word linear includes the word line. Now, formally, as we saw earlier, m itself can be defined as not y, m delta y over delta x. You may remember this from high school as the rise over the run. So you're intimately familiar with linear functions. So that's good because in the real world, many of our applications are based on linear functions. And we saw this earlier. And for any 2 points on a straight line, we can easily calculate the slope as the change in the y's over the changes in the x's. So there will be 2 points, and we'll arbitrarily choose one of them to be 0.1. And the other one will be, of course, 0.2. It doesn't really matter which is which. We'll still get the same result. Okay. So here's a good one. What's the slope? Well, and this graph, and this is Excel, so it looks a little clunky, but I picked 2 points, 7, 0, and 6, -1. So we can think of these as x1, y1, x2, y2. And watch how easy this is. And that, in turn, is simply -1 minus 0 over 6 minus 7, which is -1 over -1, which is +1. That's the slope. That means every time x goes up by 1, y goes up by 1. Every time x goes down by 1, y goes down by 1. And you can tell, I mean, remember the original function was y equals x minus 7. Don't forget, when you write out x like this, there's an implied coefficient of 1 here. So if y equals mx plus b, it must be the case that m is 1 and b is -7. Okay, so that's how you can immediately interpret what's going on with a linear function. By the way, there's more than one way to write this. This is just the one you're probably the most comfortable with, but there's another way, which we'll see in a little bit. And so because of that, we're going to call this one the slope-intercept form because it shows us the slope and the intercept. So you might say, well, what else is there? But when you see the second approach, you'll probably recognize it as well, because what it essentially involves is just the slope and one of the points. But here, I think this is the one that we're the most familiar with. Okay, what else do we need to know here? Oh, I just wanted to point out here that it doesn't matter which point was 2 and which was 1, we'll still get the same result, which is good. Okay. Now, you can tell a lot about a function by the slope. If the slope is positive, then you'll end up with something like this. If the slope is negative, it'll look like this. And if the slope is 0, you'll end up with a flat line. Okay, so let's remember that. Positive slope means it moves in the upper right-hand direction, negative down to the bottom right, and 0 means it's a flat line. Okay, not that, I mean, the drawing is not very good, but it's a flat line. Now let's look at this one, y equals 3x minus 2. Why don't we put it in symbol lab? 3x minus 2, very similar to the one I chose. And, well, what do you know? Now, first of all, the slope is 3. The intercept is -2 right there. Okay, so in other words, the vertical axis is where x equals 0, y equals -2. That's the intercept. Or at least we should say it's the vertical intercept. There is a horizontal intercept as well. This is where y equals 0. That would be considered the solution of this line. That means that when x is 2/3, y is 0. All right. Yes, exactly. Now this one is downward sloping because the slope is negative. Let's take a look at it. -4x plus 5. Oh, just as we predicted, it's downward sloping. The intercept is in fact 5. So there should be no surprises there. And this is the Excel version. It's a little awkward, but you can see what you need to see. And then finally, the case where their slope is 0, well, we're just going to have y is equal to a constant. Like, for example, y equals 1. M is 0, which is why it's missing from the equation. So what does this thing look like? It should be a flat line. There it is. There's no slope. Well, the slope is 0. The intercept is 1. All right. That's what it's supposed to look like. Now, I mentioned before, there's an alternative approach to doing this equation. And you can see it's something you might not have seen before. Essentially, what you're including in this equation is 1 point and the slope. So in order to uniquely identify a linear equation, you either need to know the slope and the intercept or the slope and 1 point. This is the one you might not have seen in high school. They may have saved this because it's a little bit messier, but it has its uses as well. And you can see that the way it's written, the slope is y minus y1 over x minus x1. So let's try one of these. And what we're basically going to do is turn this into our old familiar slope intercept form, okay? So in other words, imagine if you bumped into this one. Ooh, y minus 4 equals 2x minus 5. That doesn't look like anything we're familiar with, does it? But what it tells us is that this function has a slope of 2, and it contains the point -5, comma 4. Sorry, that would actually be positive because we're subtracting it. 5, comma 4. Now, just out of curiosity, I want to see how Symbol Lab reacts to this. If I write it like this, let's see how smart it is. Y minus 4 equals 2 times x minus 5. I want to see how smart this is. Well, it's expressing it like that. You can see algebraically, this is 2x minus 6. So all we did was rearrange it algebraically. Yeah, you got it right. You can see the intercept is -6, the slope is 2. Although it's written like this, it's the equivalent of 2x minus 6. So in other words, just be aware that this and this mean the same thing. Now, you might not think so, but each one of these will be useful under different circumstances. It's not the case that one is always better than the other. It depends on what we're trying to figure out. Okay, so let's see what's left. Oh, there's so much more to go here. This is actually a fairly one of the quicker chapters, but ooh, we have applications from economics here. And we're going to get some practice graphing. So this will actually be kind of a fun chapter. Yeah, although no, there's all kinds of nice topics coming up here. I love the idea that we have all these wonderful applications in here too, which is very helpful, I think. Because chapter 3, I think we're going to start looking at exponential functions, which it's a little more challenging, but it's also extraordinarily useful. Oh no, that's next. 3 is polynomials. Okay, so all right, I think we've had enough for one day. So mostly, I mean, make sure that you go back to Moodle, which I've long since lost. I know it's here somewhere, but if you look at Moodle, there is a second and a third problem set for this chapter, chapter 1, I mean. I'd like you to have them ready for next time. And we'll go through them and make sure we're all on the same page. And if not, oh, here it is. We can start making arrangements for Zoom sessions, okay? Or, you know, if you don't want to wait that long, you can we can do that even before we meet next time. But we'll probably not be done. We might finish 2 next week. And if we do, we'll just briefly start 3, which again is our discussion about polynomials, which basically means functions that have many terms, which means we're including like quadratics and cubics and all this and that. So it gets a little bit more intense, but we'll be fine. Okay. So, all right. So why don't we stop right here before we die of exhaustion? And all right. So is there any last minute questions? Okay, so in the meantime, why don't you read through the slides and make sure you understand what we've done. Go through it as slowly as you need to, and then work on those problem sets and see if you can still make sense out of them, okay? All right, so I guess I'll see you all next Wednesday then.
Thank
Okay.
you.
All right, bye.
Thank you, Professor.
Okay, bye.
I'll make sure to email you if anything.
Okay, good.
All right, take care.
All right, bye.
Bye.
I actually do have a question.
Okay,
I missed out I missed out on the first chapter of homework because I normally go to a tutor and none was available at the time. And I was wondering, I'm not asking for extra credit or anything. Where do we where do we even submit the homework area?
oh no, these were not supposed to be submitted. This was just practice.
Oh,
Yeah,
okay.
no. So yeah, you're all set. No, it's just
I still
this is-
plan to do it, and because
Oh,
But I
well,
was
you know,
just
you
wondering
can just do the problems and look at the solutions, because I'm going to post them in a few minutes, and make sure you're getting the same solutions. If not, you can ask questions the next time we meet. But if you're getting the same answers, then you're all set.
Okay, I just want to be clear on that.
Yeah.
Thank you, Professor.
Okay, you're good. You're right. I'll see you next time.
You too, man.
Okay, bye.